let's have a quick look at the periodic table. Well, here's a periodic table right here. This is the periodic table of the elements. Now, Dmitry Mendeleev gave us this idea of this periodic table in 1869. So we've been using it quite a while now, and that should give you some indication of just how good it really is. Now, this is how the periodic table is usually presented, but actually it's more like this. Okay, so if we just go back to that original slide, these lanthanoids and actinoids down here, the green rows, they are actually part of the periodic table. If you follow the asterisks, here we go, single there and a double there. Yes, well the single, that's where the lanthanoids fit, and the double asterisk, that's where the actinoids fit. So they do actually fit into the table, they do slot in there. So this is what we refer to generally as the extended periodic table. But you just need to keep in mind that those, the two green rows, and they're only green on this example of a periodic table, quite possibly on the periodic table that you have, they won't be green, but this is color-coded for a reason. We'll get to that in a sec. But those actinoids and lanthanoids are part of the periodic table and they fit in there. So why the heck would we pull out those lanthanoids and actinoids? Well, it fits on a piece of paper. Basically, that's actually what it comes down to. That extended periodic table, it's not very high, but it's very, very wide, isn't it? Yeah, so to fit on a piece of paper nicely, we pull out the lanthanoids and actinoids. So, Grant, that's the first thing to note. They're not down the bottom because there's anything wrong with them, they're just making the whole thing fit on a piece of paper. Great. Now, as we look along the top of the periodic table, we see some numbers. This is the group number from 1 to 18, right? There are 18 groups of the periodic table. Now, a group is a vertical column, all right? So, group 1, all of these, okay? Hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium, they are group 1 elements. Whereas something like, or where should we go, boron, aluminium, gallium, all these elements are group 13, okay? Chromium, molybdenum, tungsten, etc. These are group 6 elements. So a vertical column is described as a group, or called a group, right? 18 groups of the periodic table. Now, a horizontal row, well, that's a period. So down the side of the table, on this table it's listed the period number. It often isn't actually listed. The group number should usually be listed, but the period number often isn't. But so we can see in the first row, the first period, we have hydrogen and helium, whereas sodium, magnesium, aluminium, silicon, phosphorus, etc. are all in period 3, the third period or the third row of the periodic table. Okay, so we have a vertical column as a group and a horizontal row is a period. Okay, let's do some naming of certain groups, shall we? Let's just move the table down a bit, give us a bit more space up top. Well, the lanthanoids and actinoids kind of take care of themselves, right? They have already been separated, so we don't have another name for them. We just call them the lanthanoids and actinoids. Great. Group 1, well, we've got a name for them. Group 1 elements are called the alkali metals. Alkali metals. Group 2 elements down this column, their name is actually fairly similar. Instead of the alkali metals, it's the alkali... Oh, wait, no, we needed to change it. It has to be a different name. Well, let's put an N and an E. Instead of the alkali metals, it's the alkaline earth metals. Okay, so a bit of a similar name, but there we go. Alkali metals group 1, alkaline earth metals group 2. Now we're going to jump on over to the other end of the periodic table. Group 18 elements are the noble gases. Okay, so they are all gases. Now what's this noble mean? Well, noble doesn't actually mean that they descended from royalty. The noble gases just don't do anything. They're very unreactive. Okay, so we call them the noble gases. Group 17, they have a name as well. They are the halogens. All right, group 17, if you're in group 17, you're referred to as being a halogen. Now, a halogen means salt maker. Okay, gen from Genesis, to make, and halo meaning to do with salt. All right, now the deal with these guys is that they will quite happily react with positively charged ions, with cations, like from the alkali metals, etc., and they will make a salt. So examples of salts, well, here's one example, and this salt happens to have the name of salt, right? The common name. That's just one example of a salt, though. In chemistry, salts are simply ionic compounds. They are things that are made from the ion. So if we took our magnesium ion and we hooked it up with a nitride ion, we would have magnesium nitride, and that is another example of a salt. Okay, we could have sodium instead of chloride. We could have sodium fluoride. We could have rubidium iodide. Okay, these are salts. So there we go. The halogens, meaning salt maker, that's group 17. And where else can we go? Well, let's go to this big red block. Actually, we should have talked about the color coding on this, but that's okay. We will in a sec. This big red block, these are the transition elements. Now, they're all metals, and as such, they are often called the transition metals. Okay, so it doesn't really matter whether you call them the transition elements or the transition metals, same. Okay, there we go. Now, there are actually a couple of other names that aren't in common usage. Group 15, these guys here, are called the pnictogens, from the Greek pniktos, meaning to choke or to stifle. You'll notice that nitrogen is at the top. Well, molecular nitrogen has the property that it will basically choke you out, snuff you out when there's no oxygen present. So that comes from the Greek pniktos, meaning to choke. So the elements below that whole group, are known as the pnictogens. Group 16 are called the chalcogens. The thing about these guys is that, well, actually the thing about the ores, the rocky ore found in the Earth's crust, are mostly oxides and sulfides. So group 16 elements are called chalcogens because that means ore forming. Okay, so the halogens, salt forming, the chalcogens, group 16, ore forming, because most ores of the Earth's crust are oxides or sulfides. Group 15, pnictogens. Now, the thing about those is they are often not mentioned at all. They are official names recognized by IUPAC. All right, hopefully you should know who IUPAC is. IUPAC is the International Union of Pure and Applied Chemistry. They basically give us all the guidelines and rules that we need to follow when we're doing chemistry. There's a physics version as well, the IUPAP. All right, so, but generally we don't go into chalcogens and pnictogens. We just talk about the alkali metals, the alkaline earth metals, the transition elements, and then we jump across to group 17 and 18 for the halogens and the noble gases. Now, I did refer very briefly to the color coding that we can see on the table. What the heck is that about? Right, so if you ask for the electron configuration of something, let's say aluminium, the electron configuration 283. Great, that's lovely. If you have taken that next step, and instead of 283, if you're writing it as 1s2, 2s2, 2p6, 3s2, 3p1, if that means anything to you, well, that's the color coding on this periodic table, right? If you know about SPDF with the Aufbau electron configurations, blue elements are the S block, the yellow is the P block, the red is the D block, and the green are the F block elements. Okay, so this periodic table happens to be color-coded according to the S, P, D, and F blocks. But if you haven't gone into that version of the electron configuration, don't worry. It is a more senior version. If you're sticking with the 283 for aluminium, that is perfectly fine. And in terms of the color coding on this periodic table, you can completely ignore it. If, on the other hand, you are doing the Aufbau electron configuration, the color coding is quite handy to remember the blocks because it tells you where to stop, right? So, for example, if you were writing the electron configuration of iodine, you would just follow your Aufbau roadmap. And where do you stop? Well, it's a P block element. So, actually, let's just keep it aluminium. We're doing iodine's electron config. So, it's a P block element. It is the 5th one along, so it's a P5, and it is in which row, which period? Well, it's in the 5th row. It's going to finish with 5P5. So if you were writing electron configuration following your Aufbau roadmap, you can just throw them down, fill up the S with the 2, the P with the 6, the D with the 10, and the F with the 14, and then you would stop at 5P5. Okay, so knowing the SPDF blocks tells you where to stop when you're writing the electron configuration. So it's quite handy in that respect. Right, each square. Let's look at what does the square of the periodic table tell us. Well, there are 4 parts to this. This first number up here is the atomic number. Now, the atomic number is, of course, the number of protons. Right? Number of protons is the atomic number. Now, the symbol for the atomic number is capital Z. All right, that's actually from the German Zahl, meaning number. So, first one there, atomic number. The second thing we can note here, well, that's the symbol of the element. All right, symbol for hydrogen is H, symbol for lithium, Li, symbol for beryllium, Be. Now, when writing the symbol, we always have a capital at the start, and if there is a second letter, and in hydrogen's case there isn't, but lithium and beryllium there is, it has to be written lowercase, right? So that's the convention for writing the symbols. Start with a capital. If you have another letter, it is lowercase. Underneath the symbol, we see here the atomic mass. Atomic mass. Now, the symbol for the atomic mass is A. Again, from the German, I can't remember the word off the top of my head, but don't worry, trust me, it's a German word. It starts with an A, right? Now, the atomic mass is essentially the mass of an average atom of that element. When we're working out this mass, we completely ignore the mass of the electron because they're just so much smaller than a proton and a neutron, right? They're 1,836 times less massive, so it's pretty negligible, right? So that's the atomic mass. Now, that can also be referred to as the mass number. Okay, let's just put in brackets here. Mass number. Now, the mass number, we can call it that when we're talking about how many neutrons are there in an atom of this stuff. Okay, so the thing about that is that you have to round to the nearest whole number. You cannot have 0.008 of a neutron. You either have one or you don't. Okay. Now, the reason that it's a decimal number for the atomic mass is that's actually the weighted average of all of the different isotopes in the universe of that element, right? So I've got another video on isotopes. You can watch that as your leisure. But in terms of mass number, if you're working out how many neutrons an atom has, you just round that atomic mass to the nearest whole number. Then you can call it mass number, which is, of course, the number of protons plus neutrons, right? Number of things in the nucleus, number of nucleons, we call them. Okay, grand. Now, underneath that, we have one more thing. Well, that's pretty self-explanatory. Hopefully, that is the name of the element. There we go. Now, actually, looking at that, the name and the symbol, if we go back to a nice clean periodic table, we'll note that a lot of the time the symbols just make sense, right? Hydrogen, H, that makes perfect sense. The next one, helium, H. No, wait, I can't use an H. That was hydrogen. Well, okay, we'll use He. See how that just makes perfect sense? Lithium, Li, beryllium, Be. What else have we got? Cobalt, Co. Titanium, Ti. See, a lot of them just make sense. But then you have the ones like sodium and potassium, the things that just don't seem to make sense. Copper, Cu, right? Well, why not just C? No, that was carbon. Well, why not CO? No, that's cobalt. Well, that's lovely, but where the heck does the U come from? Sodium, there's no A in sodium. There's no N in sodium, and yet we have this big symbol here of an Na. Well, when the symbols don't seem to make sense from the name, that's because it's from its original Latin name. Right, so like sodium used to be called natrium, and when you know the original name, suddenly that Na, it makes more sense, doesn't it? Potassium used to be called kalium. Okay, so there we go. What am I doing? Not the Ka, just the K makes perfect sense, right? A K for potassium, for kalium. In terms of copper, well, copper used to be called cuprum, spelt with Cu, right? So Cu, prum. So the elements that don't seem to make sense, that explains that, right? So like we have iron used to be called ferrum, right? What else have we got? Tungsten, where's the W? Here's the W. W for tungsten, what the? Yeah, it used to be called wolfram. Okay, so some elements just make sense, and the ones that don't, it's just from its original name that it used to have. All right, now where did we actually get this table from? Well, as mentioned earlier, 1869, we should probably write the guy's name, Dmitry Mendeleev. All right, so we've got Dmitry. When you're writing it, it looks like Mendeleev, but when you're saying it, you say Mendeleev, right? Dmitry Ivanovich Mendeleev. In 1869, he actually gave us this idea of the periodic table. Now, he did not know all of these elements, right? There are 118 elements on the periodic table. He didn't know that. In his day, in Mendeleev's day, he knew sort of 60 odd. I think it was low 60s. So the story is that he actually stayed awake for 3 days and 3 nights. And then I guess he was really, really tired. So he fell into a deep sleep and had a dream. So he dreamt up the periodic table. When he woke up, I guess he reached for his notepad and pencil and scribbled it down. Right? Now, he didn't know all the elements, but what he did was he left gaps where he thought there should be an element. So he actually made predictions that one day this certain element would be discovered and it would have these certain properties. Well, that was grand because later on these elements actually started to be discovered and they fit the table just where Mendeleev had predicted that they would, and they had the properties that he had predicted they'd have as well. So it turned out that Mendeleev was quite the genius, right? He was a Russian chemist, gave us the periodic table in 1869. Now, Mendeleev didn't actually get it completely right. Mendeleev actually arranged the elements according to their atomic mass. Now, of course, we arrange it according to atomic number. Moseley worked that out in 1913, that's actually the better way to do it, and sure enough, it was. So that's how we now do it. But essentially, the table didn't really change because as you're increasing atomic number, you're also increasing the atomic mass. So it still worked out. But we do say now that it's organized according to the atomic number. But anyway, there we go. Dmitry Mendeleev, Russian genius chemist, gave us this periodic table in 1869. Alrighty, is there anything else we can say about the periodic table? Well, actually, yeah, there is. Let's draw a line between boron and aluminium, and then we'll draw one down between aluminium and silicon. Now, if we keep this pattern going, let's go across, down, across, down, across, and then we're going to finish with a down, down. There we go. There's something else we could mention, because on the right-hand side of the periodic table, all of these elements, these are the non-metals. Right, these elements are non-metallic in nature, okay, so they do not have metallic properties. And therefore, on the left-hand side of that little zigzag stepped line, we have the metals. There we go. So we've separated the metals from the non-metals. That's something else we could do. Something else we could do, I tend to not usually bother, but some people do. Let's just get rid of this. There are actually a few elements sort of either side of that metal, non-metal, zigzag stepped line. There are a few elements either side, elements like boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and I believe astatine off the top of my head. These elements actually have some properties of being a non-metal, but they also have some properties of being a metal. So they're kind of a sort of a metal, which is why they are referred to as the semi-metals, because they actually have properties of both metals and non-metals. Their proper name is metalloids, but you often see them written as semi-metals. Well, I say often. Some tables show the metalloids or semi-metals. Other tables don't really bother. I tend to not bother splitting them up because we don't really go into the metalloids very much at all. It's good to know, oh yeah, this one's a metal, this one's a non-metal. So I just tend to do this line here. Okay, cool. So, was there anything else? Well, actually, there is one more thing we could mention. We could take a bit of a look at some more of the element symbols. So we mentioned some of them just don't seem to make sense. Like, what the heck, AU for gold? Well, gold used to be called aurum, so hence the AU. So yeah, we didn't mention all of the elements that the symbol doesn't seem to make sense, but remember it comes from its previous name. But what you'll note is that you will not see a J on the periodic table. You will not see a Q on the periodic table. And another thing we will notice on the periodic table is that some of the names sound familiar. Like, for instance, Californium. Well, that sounds like a certain place, doesn't it? Some of the elements are named after places or people. Okay, Curium, that's named after Marie Curie. We have Einsteinium. No prize is awarded for guessing who that one was named after. Copernicium, that's named after Nicholas Copernicus. Moscovium, that's named after a certain city in Russia. Morganison, that's named after the Russian who discovered that one. So this is fairly frequent, that a lot of the elements are named after places or people. Here's another Francium, just jumped out at me. That's named after France, obviously. But there are actually two elements which have countries named after them. Now that's a bit of a strange one, because usually elements are named after the country, right? Elements are named after places or the people. It's not usually the other way around. So two elements have countries named after them. Can you work out what they are? Drum roll, please. And the answer is silver and copper. Here we go, silver. That's one of those, hey, wait, the symbol doesn't make sense. Yeah, but it's old name. It used to be called Argentum. Can we guess the country? Well, Argentum. People moved in that area, found lots of Argentum, and then decided to call the place after it. So they called it Argentina. And copper used to be called cuprum, right? That's why we get the CU from cuprum. Well, Cyprus is actually named after that. When people moved there, they found lots of copper, so they called the place Kypros. So Kypros is named after cuprum. Now, of course, we don't say Kypros, we say Cyprus. So there we go. There are actually two countries named after elements, when usually it's the other way around, where the element is named after the place or the person. So there we go. I think that's a done deal. Let's call that your intro to the periodic table of the elements.
Don't forget to hit the like button. Yeah. And subscribe to It's Up Here. And here's another video.